Now we saw earlier that light is what we call an electromagnetic wave. So normally when we think of light, we think of just the visible part of the light spectrum that we can see, but light is actually composed of a whole bunch of different kinds of electromagnetic waves, including things like radio waves and microwaves that we can't see. Often people refer to light as just the visible part. I'll try here to make sure that when I'm referring to just the visible part that I call it visible light. So this electromagnetic wave is, as the name seems to suggest, is a fluctuation of electric and magnetic fields. Now, we don't see these individual fields. We can't see electric fields and magnetic fields. We only see the result of that fluctuation, which is the light itself. Now, light doesn't have any mass. And so it's not affected by gravity in the normal sense that we think of things being affected by gravity as a mass falling towards the ground. The reality is way more complex. It has to do with Einstein's theory of relativity, and we don't get to that in any high school courses, and even most university courses probably wouldn't touch on that. So for all intents and purposes, we say light is not affected by gravity. As a result, if it's not going to be affected by gravity, it travels in a straight line. So if I were to throw my marker here that I'm holding in my hand, it will eventually come down and hit the ground. It's going to follow a curved path. We call that projectile motion because it's affected by gravity. If I fire a bullet out of a gun, even like a high-powered sniper rifle, it may travel way further, but it will eventually, if it doesn't hit anything, eventually hit the ground. Now, light travels even faster than that, but even if Earth was big enough that light would have had time to hit the ground, it doesn't because it travels only in a straight line because it's not affected by gravity. So we call this linear propagation. If we want to get more technical, we call it rectilinear propagation because of the fact that the electric and magnetic fields and the path of the light are all at 90 degrees to each other. Well, we'll just call it linear propagation for now. So a single beam or a single wave of light is referred to as a light ray. They are thin. They don't have any specific value in terms of their size, but we want to look at a light ray. We're going to assume that it's really, really, really thin, and as we said before, travels in a straight line. And the result of this, we can see in our everyday lives, things like shadows and pinhole cameras. Not that pinhole cameras are very common anymore. Well, let's take a look at what this looks like in terms of shadows, because we've all seen shadows before. So the shadow that we get really depends on what kind of light source that we're looking at. If we have a point light source, which is like a really small light source that's only emitting light from one point, one local point, then what we're going to get is a really crisp shadow. So let's draw a little light ray coming out from this little line over here. That's way too thick. So let's back this up and let's do that. So here's a light ray coming from here and just nipping the top of that wall. So that light ray, we'll draw little arrows on there to show which way the light is going. That light ray the light from that point source coming from, say, here towards that point, that light ray is going to hit the wall and not be able to go any further. So none of this stuff over here is going to be able to be lit up by that point source. And then all of a sudden, the light rays can make it past the wall, so everything past this point is all lit up. So this is obviously what we call a shadow. And it would give a very, very crisp shadow if you have a really small point. A diffuse light source is one that has a little bit of thickness. The lights in our classroom are very, very diffuse. They're really long lights. There's light coming from all over the place. So let's take a look at this light ray here. So let's say we're looking at the light ray coming from near the top of that light source. It's going to hit the top of that wall. If we draw a light ray coming that just nips the top of the wall, everything to the right of that light ray, where that light ray hits, everything to the right of this point right over here will be lit up, and everything to the left will be in shadow. However, if we now look at, and I'll draw this in a different color. Let's make it pink. So if I draw that light ray coming from down here, and it hits the top of the wall, it's only going to hit the ground way over here. Let's extend my line a little bit. So for that red light ray, everything out here is lit up, and everything to the left is in a shadow. For the green light ray, everything out here is lit up, and everything to the left is a shadow. So you can see that no matter where the light's coming from, we're going to get our shadow in this area over here. But there's a transition area from there to there where it's kind of partly in shadow. Some of the light rays make it, some of the light rays don't. So we have different names for these. This part here is called the umbra. This part here is called the penumbra. We use these terms a lot when we're talking about solar eclipses, because the sun is a little bit of a diffuse source when the moon is cutting in front of it. So there'll be parts of Earth during a solar eclipse that will only be partially covered. Well, the moon will only partially cover the sun. And if that's the case, then we would say we are in the penumbra of the moon's shadow, as opposed to the umbra, where the entire sun would be blocked off. So there'd be a gradual transition from that point over here, where it's really, really dark, and it'll get lighter and lighter and lighter until we get to that point over there. So that's why some of your shadows look a little bit fuzzy, because we're going from being the umbra into being in the penumbra. Where others, shadows will look very, very sharp. The shadow I'm getting right now, which you can't see, but the shadow I'm getting right now from the projector is an extremely sharp shadow, because the light is mostly a point source. The shadow that I get from the lights in the classroom is very spread out, so I have an obvious umbra and penumbra as well. Now, a pinhole camera is a really neat thing. Once you've watched this video, ask your teacher to let you take a look at the pinhole cameras that we have in class, and you can go out into the hallway, take a look down the hall towards the window, and see what you're going to be able to see. So we have, let's draw another light ray here. Let's make it red again, coming from the very top of this object. So the object here, we'll label it as an O. It's nice and easy to draw an arrow, because they're easy to draw, but it's very obvious which side is up, as opposed to drawing something like, say, a person or a tree, which is a little bit more complicated to draw. So we try to keep it nice and simple. So let's say I have a light ray coming from the top of this object. Now, this light ray is going off in all different directions, but we're going to concern ourselves with the one that's going to go through this little hole in our pinhole camera, and it's going to strike the back of our camera. And maybe we have a little piece of film there or something like that. Let's now look at another light ray. We'll draw it in green again, coming from the bottom. I hope I drew this well, and it looks like I didn't. Just maybe have to pretend and use our imagination a little bit. So the light ray coming from the bottom is going to go through that same hole, but you can see that it's going to end up hitting the film at the top. So let's just extend this out a little bit. There we go. And so it hits at the top. Now, if we draw where our image is, so the image is where the light rays go. Our image, which I'll draw in blue over here, this is the bottom of the object, and here is the top of the object. So you can see the image that we make on the film of our pinhole camera is upside down. We get a lot of this, actually. As you may see later on, that the image that we get inside of our eyes are upside down, and our brain just flips it over for us automatically just to kind of help us out a little bit. And that's what a pinhole camera will do. It'll give an upside down image. So try this out with the pinhole cameras in class when you get an opportunity. So when we have visible light and it strikes a material, as we kind of alluded to a little bit with the shadows, there's actually one of three things that can happen. The first thing that can happen is that the light can be transmitted. Transmitted means that it goes through the material, right? So air, glass, things like that. It can also be reflected. So the light ray, I'll use quotation mark because it's not actually what's happening, but it actually bounces off the surface and it'll reflect in a very specific way, which we'll talk about later. And the last one, which we really won't get into very much here, is that it can be absorbed. So all of its energy usually goes into heating the material. And this is why when you leave your car in the hot sun all day, when you come back to your car, it's really, really hot because the light rays have been absorbed by the car. So which one of those three happens really depends on the material. And we have three names, which I believe you've seen in maybe elementary school, for the types of material you have and whether light passes through or not. It can either be opaque, it can be transparent. In opaque materials, no light can get through, and it's either going to be reflected or absorbed, usually both. Transparent, light will go through. It may also be reflected, and it could also be absorbed as well, but at least some of the light goes through. And translucent. And in translucent material, we need to know, in fact, we always need to know a little bit more about our materials and see whether they can go, the light can go through it or not. What usually happens is more than one, and in fact, maybe all three things can happen. Some of the light ray gets transmitted, some of the light ray gets reflected, some of the light ray gets absorbed. So yeah, we talked about some examples. So for glass, light ray hits the glass, it is transmitted. Some of the light is transmitted because the glass is transparent. But some may also be reflected. Those of you who wear glasses may notice that at the edges of your glasses that you see little reflections as well. They're kind of annoying. That's because not all, now, glasses are normally made of plastic and not glass nowadays. But it doesn't change the fact that you get a little bit of reflection. And you might also get a tiny little bit of absorption. Not very much, though. Whereas the surface of the desk in your classroom or any solid material like that is opaque, it's going to definitely have some reflection. As I look at the black desks in the class, I can see a little bit of light reflected. I can't really get a great image of the light, like it's not like a mirror, but I see that there is a little bit of light that is reflected. If there's no light reflected, then no light can get to your eye and you wouldn't be able to see it. So there is a little bit of reflection, and there is quite a bit of absorption as well. But we don't get a whole lot of transmission, at least not with visible light. So we're going to choose to focus on the reflection part of this, the absorption and transmission. Well, transmission we'll get to a little bit later on in another video. The absorption we're not going to touch on at all in this class. And so let's just look at reflection for right now. So if the material is opaque, it's going to reflect at least part of the light. Now, how it reflects that light depends on whether the surface is smooth and if it's smooth, then you just get regular reflection. If the surface is rough, then you get something called diffuse reflection. So imagine that you've got, say, a surface that looks like this. It's rough, it's bumpy. Even the smoothest of surfaces, right now I'm touching a textbook at the front here and it feels pretty smooth, but even the smoothest of surfaces at a microscopic level is going to be very, very bumpy. And so when light rays come in, they will bounce off in different ways. That one might bounce this way. Another light ray might be coming from here and bounce that way. It might be coming from here and bounce that way. So you get light rays going a whole bunch of different paths, which makes the reflection not very sharp. So you would never make a mirror of this. This is the type of reflection that I'm seeing off the surface of the black desks here in class, and that's why I don't get a really sharp reflection. So that's why I can't treat it like a mirror. A mirror, on the other hand, will give you regular reflection. At least a good mirror will. And if we measure the angle the incoming ray is called the angle of incidence, and we're going to hear that language, that term a lot in this unit. The angle of incidence is the angle that's coming in, and then you have a reflected ray that's coming in at a certain angle called the angle of reflection, which makes a lot of sense. So in every case, the angle, a little symbol for angle there, the angle of incidence, which we'll call I, is equal to the angle of reflection. Always. This is universally true. And we call this the law of reflection. So, I mean, it kind of makes sense. If you like to play pool, billiards, you'd probably use something like this, where you will bounce balls off of the rail. Maybe you're making a bank pass off the boards in hockey or in basketball. Now that reality can get a little bit trickier because of the spin on the puck or the ball will cause it to come out at some weird angles. Light doesn't have a spin, so it won't spin off of a surface. So we get this angle I equals angle R all the time. Now, one of the unique things that we do with light rays is we don't measure it from the surface itself. We measure it from this imaginary line that is perpendicular to the surface, and we call that line the normal. If you end up doing any higher level of math, then you'll hear this word normal. If you end up doing grade 11 physics, we will talk about normal forces. And the word normal in a mathematical sense doesn't mean regular. It means at 90 degrees to the surface, perpendicular. So the normal line on this mirror that I have drawn at the bottom of the page, the normal line, it just draws a dotted line. Dotted lines generally mean not actually there. So that line is, there's no line there, but that's where the normal would be. So what we're saying is, when a light ray comes in at a certain angle, we'll say right to that point right there, it's not a particularly straight line, but you get the point. So this angle here, which we'll just call I, we'll get rid of the little angle sign, is the angle measured to or from the normal. It will then reflect at an angle of reflection, and if drawn to scale, angle I will equal angle R. So why do we use this normal? Why can't we just measure from the surface? Because if that's 90 degrees here, then this angle, we'll call that theta, because theta is a variable that we usually use for angles. If you haven't seen it yet, you will eventually. So if this is really 90 degrees here at this surface, then that angle theta and this angle theta are also the same if I and R are the same. So why don't we just measure it from the surface? Isn't that a lot easier? Well, it actually turns out to be maybe easier in the case of a flat surface, but what about a surface that goes like that? So now you've got a light ray coming in and hitting this. Measuring the angle in here is difficult because of the curvature of the surface. But you can always draw a normal, and that normal would go straight through the center. If this was a circular object, let's say it's a round sphere, round shiny sphere, and the light is going and hitting the surface, we draw a line to the center, it will hit the edge at 90 degrees. That's one of the properties of circles, is that any line going through the center will hit the surface at 90 degrees, which means that if this is 90 degrees there, then it's also 90 degrees there. So that's our normal, which means we can measure our angle I in there, measure the same angle R in there, and it reflects in exactly the same way. So we're measuring our angles here and here instead of trying to measure to a curved surface, which is difficult. So let's put this into practice by drawing what we call a ray diagram. And again, this is something else that you'll see in future videos as well. Ray diagrams in plane mirrors are a little bit different than the ray diagrams in curved mirrors and lenses that we're going to look at. So I've kind of pared this down to like 5 steps that you need to do to draw a ray diagram. So I've got my little ruler up here on the screen. This thing here, believe it or not, is an eye, and this is some object that we're looking at. Now, in this case, you might be able to look straight at the object. Well, if we looked at it through a mirror, so here's where our mirror is. The little black lines on the other side of the mirror show that the reflective coating, the reflective surface is on the top. So measure the perpendicular distance from the object to the mirror. So I'm going to slide my ruler over. This might not be exactly what yours says, but I'm going to put my 0 mark right on the bottom of that object, and I can see that it looks like it's about 3.5 centimeters to the middle of that black line there. So to my surface, it's about 3.5 centimeters. So now what I'm going to do is I'm going to take that and I'm going to draw my 3.5 centimeters. And so step 2 is to draw the image in equal distance on the other side of the mirror. So I'm going to draw the point that's closest right about here. I'm going to move that away. And so I could draw a little circle that is approximately the same size as our object. I'm going to color it in. You don't need to. So this is our image. When you look into a mirror, if this is my eye and I'm looking at this object in the mirror, the image that I see, I'm actually seeing this thing down here. So let's look at the path that the light rays take to get to my eye. How am I going to figure that out? Now, I could use the law of reflection, angle of incidence equals angle of reflection, and kind of try trial and error until I get it right. So, I could say, all right, well, what about this? Let's draw these as red lines here. Well, what if I went over here? Okay, so let's get out a protractor and measure my angle of incidence and then draw my angle of reflection, and I might see that it comes out there. Oh, that doesn't work. And I could try trial and error over and over and over again, and that's not going to be very effective. So here's a little trick. So draw your line from your eye to the object. Now the last part of that should actually be a little dotted line. It'll be easier for you. So you should grab a ruler, pause and go grab a ruler if you don't have one right now. Anything with a straight edge will do. And connect the eye to the object. And when you're drawing your line, draw it as a solid line on the side of the mirror where the object is, and a dotted line. And what I'm going to do is I'm just going to kind of draw a little dotted line kind of overlapping, And we take this line here and shorten it up, right, like that. So that's what your line should look like. And now, so that was step 3. Now we want to draw a light ray from the object to where that light ray that we just drew hit the mirror. So from the object here to that point right over there. The last thing we want to do is draw our arrows on our light ray in the direction light is actually traveling. Now, this object might be emitting its own light, it might be reflecting light from something else. In any event, the light, it has to come from the object, it hits the mirror, right there, and it bounces towards the eye. If this is done properly, you should be able to measure, if you draw normal, you should be able to measure that your angle of incidence, sorry, that should be an eye, your angle of incidence here is equal to your angle of reflection here. If everything is drawn perfectly, that should be true, and you've never actually had to use a protractor. So the light ray comes from the object, it hits the mirror and goes towards your eye. If you reverse the arrows, it's like your eyes are shooting out lasers, which would be nice to be able to do that, but I don't think I've ever met anyone that can do that. So, you're probably not the first. The light comes from the object to the eye, not from the eye to the object. Now, this little dotted line, well, here's the problem. Your brain is way smarter than you might give it credit for. It does a whole bunch of things without you even thinking about it, and one of the things is it recognizes that light travels in a straight line. So when you see something, you know that the path the light ray is taking to get there is straight, so you know where the object is. Now, your brain is just smart enough to trick you sometimes, because you look into a mirror, your brain says, oh, light travels in a straight line, so that's where the object is. So when my eye here is looking in this direction, and I see an object over there, it says, well, that must be that. This is the path the light takes, and I know light travels in a straight line, so this must be where the object is. So that's why your brain interprets that as, look, there it is. Now, you have enough experience to be able to say, no, it's not actually there. A part of your brain, a different part of your brain recognizes, no, it's not actually there. But watch a cat or a dog in front of a mirror, or a very, very young child who doesn't understand this, and they think that there's actually something there because their brains know that light travels in a straight line. So that little dotted line that I drew, if we get rid of that green line, the little dotted line that we drew, that represents a place where it looks like the light is coming from, but it's not actually coming from that spot. So, take a look at the at a few questions from your textbook, 409 and 420. Take a look, read through those sections of the textbook before you answer your questions. There's a plain mirrors practice sheet that will be posted as well, and you can try those. Once you're done, let your teacher know that you want to go over the solutions, and your teacher will go over it with you.